Hello. Today we are going to talk about the traverse typecast. To understand what traverse does, I think the easiest way is to look at the sequence function. So we are inside traverse of f, and there's a function called sequence that for an f of g of a will return a g of f of a. This sounds very abstract because we still don't know what f and g and a are, but as you'll see, it doesn't really matter what a is, and g can be any applicative. And what that means is, well, I'll just show you. If you've been doing Scala for at least a couple of months, you will probably have encountered future. Future is a type that encapsulates an asynchronous computation in Scala and allows you to compose these computations together. So one way to create a future is to just wrap some sort of code, like maybe a blocking action like trade sleep, which you should probably never use. And we can wrap that in a future so that it will run on a different thread than the main thread. So we will sort of lift this expression to an asynchronous computation. Of course, it will still be blocking, but it will not block our current thread, not the main thread. So for that, I will need an execution context. Let's use global. And then I can produce some sort of value in this future. Then I can create another future that will see roughly this, well, roughly half a second and produce a different number. Now, I can put these futures in a list. And if you want to run, you want to wait for a whole list of futures, you would most likely use the future.sequence function, which will just turn a list of futures or a sequence of futures into a single future that will complete with one list inside when all of these are done. So if we use this and we use await to get a result from this, and then we will print this, you will see that indeed we run both these futures. And because of the way future works, when I have created this one, it's already running. And by the time I start creating the second one, the first one might even be over. In this case, it will probably wait for a couple of milliseconds more, but still, it's already running. And by the time I construct this list, both my futures are running. They have to, because lists take strict arguments. These are already evaluated expressions. So by the time I run future.sequence, well, both my futures might be done. So I'm effectively using sequence to run my futures in parallel. Future is, well, it's eager. It starts evaluating the moment you create it. But that's not the only way to reason about asynchronous computations in Scala. Another way is to use I/O. And I'm going to use I/O from Cas effect to show what I mean. At this time, however, I won't be able to use future.sequence because, well, we don't have futures anymore. We will have I/Os. So let's rename everything appropriately. And I'm not going to use await result because that's also meant to work only with futures. Instead, I will use the traverse type class and the sequence operation. I will, of course, need some more imports and the syntax from cats, but this will work. So this will return an I/O of list of ints. And I can run an I/O by blocking the current thread and just waiting for a value to pop up. And for a while, I'm going to do that. Let's just confirm this works in the same way. So it produced the same results, but of course, previously we had futures running in parallel. Now, well, I/O runs sequentially by default. So when I created this list, I still have no computations going on whatsoever. And when I use sequence, by the definition of I/O, by the fact that it's a monad, I know that my computations, my I/Os, will run sequentially. There's no way to use sequence with the I/O type and have parallel computations. We can work around that, but that's a different video. So for now, let's just focus on sequential composition. So I mentioned that a safe run sync is one of the ways to run an I/O. It's unsafe because it breaks referential transparency and it also blocks the current thread if there's blocking inside my I/Os. And there's obviously blocking because of thread sleep. So there's probably a different way, right? And there is. Class effect provides a trait called IO up that we can mix in, and then we can just return an IO from our program, and the runtime will handle the rest. So we don't have to do any blocking ourselves. And we don't need to break referential transparency either. So I'm going to use sequence again, and I'm going to return, to convert this IO of unit probably to an IO of exit code by using the as function, which is just an alias for map with ignoring the source. So this is it, and I can now refactor. Okay, but now I only sequence the list of IOs, and I have an IO with a list, but I haven't printed it yet. So let's flat map on this IO and print the results using IO again. Okay, let's confirm that still works. Okay, so we got the same result. Great. So let's just confirm what has happened. I created a bunch of IOs. I put them in a list. Then I sequenced that list so that the result will be a single IO that will run my both IOs in a sequence, basically. And then after they both are done, all of the IOs in this list are done, I will go on with that result list and print it. And then we'll just complete with the successful exit code, which is 0. So far we've only seen sequence or traverse on a list. And actually we haven't even seen traverse yet. So let's look at the other function in traverse, which is traverse. Traverse allows us to take some sort of container of values, execute an action for each of these values, and then combine the results of this effect, this G effect, into one single effect with a sequence of results. Let's look at how that would look like in practice. Let's start by creating a list of ints. So I have 10 integers, and then for each of them, I want to run an action. So for now, let's just map these integers to something that will return an IO. So we will take an integer and return an IO string. I will pretend we are doing something clever here, some CPU or network intensive actions, but I will just sleep for a couple of milliseconds and then produce a value equal to I to string. Okay, so I still haven't used the traverse function, but this still works because I mapped my integers to the action on them. This will be, again, a list of IOs, and then I sequence that. But it turns out that map and sequence is just traverse. So I can use the traverse function like this. But so far we've still only seen traverse to work with a list. Can we use anything else? And it turns out we can. I could very easily change this to be an option of int. And everything still compiles and everything still works. But now I'll get a sum of 42. And if I make the option empty, I will get a none. So what traverse means, like in a intuition kind of way, it will take each element contained in this data structure, run an action on that element, and then combine all of the results into the same sort of data structure. So from option, we will go to option again. From list, we will go to list again. And there's plenty of more types that we can traverse on, like NonEmptyList, uh, Scala stream, and probably others as well. But probably what's the most interesting about all these traversals, is what we can traverse to. Traversing to I/O is quite straightforward and reasonable. We just run an effect for each of the elements. But can we do anything else? And it turns out we can. So let's forget about I/O for the rest of this video. Let's get back to main. So I mentioned we can do much more than just I/O. Let's create a list of options. We'll have a full option, one that contains a value. We'll have another one, then an empty option, and another full option. Let's sequence that. And this compiles. This will be an option of list. And if you think about what this function could do in the context of option and list, there's just one reasonable way to understand it. This will be an option that will be empty if there's any empty value in this list, and it will be full if all of them are full. So in this case, I expect it to be empty, just because there was one none. Let's remove it and see the result again. Now we have a sum with a list. So if you want to make sure that all the elements in your list are full, all your options, then you can use sequence to do that. Of course, if you don't want to do this, if you want to just extract the values that are not empty, then you will need to use something else. You will want to go from a list of optional string to just non-empties list of string. And this will be something like flatten option. But back to sequence and traverse, this is just one of the things that we could do with it. We can use a different data type. We can use either. So let's use either with string and int. We will have a right, we'll have a left, another left, and another right. And if we sequence that, this is going to be an either string or a list of ints. So you can see again that you can probably understand what this will do, what the sequence is going to do, because there could be only one error or a whole list of ints. And in practice, what this means is that it will either be the first left value or all the rights, if there are only rights. So in this case, we are going to have left of error 1. But if I only had rights, I would have the list of rights. Okay, but this, well, we sort of lose all the errors. We just keep the first one that we found. What can we use to collect all the values? It turns out that we can use a different data structure similar to either, that's called validated. And it works in pretty much the same way as either, but it allows you to combine errors. We will need slightly different names. Right is now not right, it's valid. Left is now invalid. And right is valid again. Okay, but this is not going to do what we want. This will accumulate errors, but instead of grouping them in a list, it will still produce a single string. And it's going to be a concatenation of all the errors which is probably not what we want. So let's wrap these strings in a non-empty list. I made it non-empty because, well, if there's a left, if there's an invalid, it's obviously going to be non-empty. There's obviously going to be something in it. So I can use invalid. I can use some slightly different syntax for this. Invalid null. That will just wrap this in a non-empty list and then in invalid. Okay, and what we should see now is an invalid with 2 elements in the non-empty list. And that's what happened. And this is really amazing because we are still using the same abstraction, sequence or traverse, but with different data types. And this behavior is guided by the applicative instance of validated. So we don't need to change anything about the implementation for list. The only thing that needs to change is, well, when we change this type inside, is the applicative for that type. So in this case, it's validated. And the applicative for validated will collect all the errors, all the invalids, and combine them using the semigroup instance for the error type. In this case, it's NonEmptyList. And the semigroup of NonEmptyList will combine this list. Just concatenate these lists. This is the same as just list, but it's going to guaranteed to be non-empty because you can append 2 non-empty lists and the result will still not be empty. So I guess it makes sense. There's no monad for non-empty list though, but we don't need it. We just need a semigroup. So this is what traverse looked like when we used it with the validated applicative. Are there any other interesting cases? Turns out there are. One of them is map. If we have a map, let's say from int to string, we will have a list of maps. I will do this with just 2 maps because it will be easier to explain. The first map will contain a mapping from, let's say, 1 to hello, 2 to world, and 3 to a bunch of exclamation marks. Then the second list will have 1 with foo, and 3 with dots, as well as 4 with anything. And now our types don't align. We need to change them a bit. We need map of int to a list of strings. And something is wrong. So we have an error here. We don't have an applicative for map. And if you don't know what that means, basically this is caused by the fact that there's no pure operation for map. The pure operation would have to look like this for any key. We should be able to write this, but it's just impossible to write this. We could, well, it's just impossible to write this, and CAS doesn't provide an applicative instance for map. But what it does, it provides an apply instance for map. Apply is just like applicative, but it doesn't have the pure operation. But it provides us with app and product, and these are the functions that we need to use traverse. But as you've seen before, sequence requires applicative. So what can we do? And it turns out that there's another type class in cats called NonEmptyTraverse. And it has very similar functions to traverse and sequence, but it also allows us to sequence using just an apply instead of an applicative. But not every type has a non-empty traverse. List doesn't have it because list can be empty, And non-empty-traverse is only available for types that are guaranteed not to be empty. But wait, we already know such a type. We can use NonEmptyList. And now this will also change to NonEmptyList. So this might be tricky, and you might not know at first what type, what's actually going to happen in this non-empty sequence. You might expect that we will get some sort of concatenation of these two maps. We will see all the keys 1, 2, 3, and 4, but that's not true. What we are going to get instead is a map from integers to non-empty list that will contain only the indexes that appear in both maps, and the values under these keys, under 1 and 3, because these are the ones that appear in both, they will contain a non-empty list with all the results from all the maps. And I can prove it to you. So you can see that we only got 1 and 3 in here. And this behavior, again, is warranted by the apply instance for map. So it's really worth knowing what these instances do. Otherwise, you might run into trouble and see something that you didn't expect. But that's just how we roll in functional programming. So this is it for today. I hope you learned quite a lot about traverse and some applicatives for some types in Scala, for some common types in Scala. So if you liked this video, please leave a thumbs up and subscribe to my channel to see more. And I'm looking forward to making more videos for you.